There are forces all around us, shaping our reality in ways we rarely stop to consider. Gravity holds us to the Earth, but another equally powerful force animates the modern world. You feel its presence when you pick up your phone and the screen floods with light. You see its work when a small magnet clings faithfully to your refrigerator door, holding up a child's drawing. You hear its voice in the music that flows from a speaker. This invisible architect of our daily lives is electromagnetism, that governs electricity, magnetism, and light itself. It is a story of connection, of how two seemingly separate phenomena are in fact two sides of the same magnificent coin. Understanding this force does not require a lifetime of study or complex mathematics. The core ideas are surprisingly simple, built upon observations we can all make. We will explore this world together, step by step, without the usual scientific jargon that can obscure the beautiful clarity of the concepts. From there, we will gently move toward the four great laws that describe this force, each with a simple equation that captures its essence. These are not just abstract rules. They are the blueprints for the technologies that define our age. From the motor that spins a fan to the waves that carry our conversations across continents. This journey is about uncovering the hidden principles behind the familiar world. It is about seeing the profound science at play in the most ordinary of objects. Imagine a world without electric lights, without computers, without the instant communication we take for granted. That was our world before we began to understand the elegant dance between electricity and magnetism. By peeling back the layers, we can appreciate the ingenuity of the human mind and the deep, underlying order of the universe. The story of electromagnetism is the story of how we learned to listen to one of nature's most powerful secrets and then used it to build a new reality. What follows is an exploration, not a lecture. It is an invitation to look at your surroundings with new eyes. Each section will build upon the last, moving from the basic concept of a charge to the fields it creates, and finally to the laws that govern their intricate interactions. We will see how a simple push or pull between tiny particles can lead to the creation of light itself, a wave of pure energy traveling across the vast emptiness of space. This is not just a lesson in physics. It is a tale of discovery that continues to unfold every single day, powering our present and illuminating our future. What follows is, an exploration. Our story begins with something incredibly small, yet profoundly powerful: electric charge. Many of the fundamental particles that make up our universe possess this property: electrons, protons. We can think of charge as coming in two distinct types: positive, negative. The first and most basic rule of their interaction is beautifully simple. Charges that are different from each other will pull toward one another: a positive, a negative. We call this attraction. Conversely, charges that are the same will push each other away: two positives, two negatives. This is called repulsion. This fundamental push and pull is the electric force. You have almost certainly witnessed this force in action, perhaps without even realizing it. Consider a simple balloon. If you rub it vigorously against your hair on a dry day, something interesting happens. The balloon can pick up tiny, lightweight objects like small pieces of paper. The rubbing has transferred charge, likely negative electrons, onto the balloon's surface. When you bring the charged balloon near your hair, individual strands stand up and reach toward it. Your hair and the balloon have opposite charges, and they are attracting each other across the small gap of air. A perfect demonstration of the electric force at work. This concept of attraction and repulsion is the bedrock upon which all of electricity is built. It is the reason electrons flow through a wire to power a lamp. A bolt of lightning dramatically leaps from a cloud to the ground. In both cases, a vast number of charged particles are being pushed or pulled by this fundamental force. Every electrical device, no matter how complex, ultimately operates because of this simple rule: opposites attract likes, repel. It is a universal law governing matter at its most intimate level, dictating the structure of atoms, the chemistry of molecules. Thinking about this force helps us understand why some materials conduct electricity while others do not. In a metal wire, there are electrons that are free to move. When an electric force is applied, these free charges are pushed along, creating an electric current. In an insulator like rubber, plastic, the charges are held tightly in place and cannot move easily. Therefore, no current flows. This simple difference, how easily charges respond to the electric force, lets us safely handle and control electricity. It all starts with that elementary push and pull. How does one charge know that another charge is nearby? How does a balloon pull on your hair without physically touching every strand? The answer lies in one of the most important concepts in all of physics: the field. An electric charge does not just sit there in isolation. It fundamentally alters the space around it. It creates an invisible zone of influence that we call an electric field. Any other charge that enters this region will feel the electric force. The field is the messenger, carrying the information about the force from one charge to another across a distance. Imagine a large, hot fireplace in the center of a cold room. The fireplace radiates heat, warming the air around it. The closer you get to the fireplace, the warmer you feel. The temperature at any point in the room tells you the influence of the fireplace at that location. An electric field works in a very similar way. A charge, like our fireplace, generates a field. We can think of the strength of the field at any point in space and the direction of the field at any point in space. A second, smaller test charge, like a person walking into the warm room, will feel a force that depends on where it is within that field. This concept of a field is a powerful tool. It allows us to map out the influence of a charge, a collection of charges. We can draw lines, called field lines, to visualize this invisible structure. For a single positive charge, these lines radiate outwards in all directions, like the rays of the sun. This tells us that a positive test charge placed anywhere around it would be pushed directly away. For a single negative charge, the lines would point inwards, showing that a positive test charge would be pulled directly toward it. The density of these lines indicates the strength of the field. Where the lines are close together, the force is strong. Thinking in terms of fields frees us from the puzzle of action at a distance. The force is not instantaneous and magical. Instead, it is local. The charge creates a field right next to it. That part of the field creates a field next to it, and so on, propagating outwards like a ripple in a pond. This propagation happens incredibly fast, at the speed of light, but it is not instantaneous. Fields are real, physical entities that fill space and carry energy. It was a monumental leap in our understanding of the universe, and it is essential for explaining static forces, dynamic waves of light, radio. That's pretty neat. Now let us turn our attention to the familiar and fascinating phenomenon of magnetism. Most of us have played with magnets, feeling that strange, invisible push and pull. Like electric charges, magnets exert forces on each other. We describe magnets as having two poles, which we label north and south. The rule for their interaction is very similar to that of electric charges. Opposite poles, a north and a south, attract each other. Like poles, two norths, two souths, repel each other. This is why a compass needle, which is itself a tiny magnet, swivels to align with the Earth's own massive magnetic field, its north pole pointing toward the planet's magnetic north. Just as an electric charge creates an electric field in the space around it, a magnet creates a magnetic field. This is the region of influence where other magnets or certain types of metal will feel a magnetic force. You can visualize this field quite easily. If you place a bar magnet under a sheet of paper and sprinkle iron filings on top, the tiny filings will arrange themselves into a beautiful pattern of lines. These lines loop from the north pole of the magnet around to the south pole, revealing the invisible structure of the magnetic field. The field is strongest where the lines are most concentrated, which is right at the poles. For a long time, electricity and magnetism were seen as two completely separate forces. One dealt with static shocks and currents, the other with lodestones and compasses. The great discovery, however, was that they are deeply and inextricably linked. The most profound connection is this. A magnetic field is produced by a moving electric charge. A stationary charge creates only an electric field. But as soon as that charge starts to move, it also generates a magnetic field. This is an astonishing idea. The simple act of motion transforms one kind of field into another. This principle is the basis for countless technologies. An electric current is nothing more than a flow of charges through a wire. Because these charges are moving, the wire carrying the current produces a magnetic field that encircles it. If you wrap that wire into a coil, you can concentrate the field and create a powerful electromagnet. You can turn it on and off simply by controlling the flow of current. This is the heart of an electric motor, a loudspeaker, and the powerful magnets used in scrapyards to lift cars. The force that was once a curiosity of nature became a controllable and immensely useful tool. We have seen that moving charges create magnetic fields. This was a revolutionary discovery, but it was only half of the story. The connection between electricity and magnetism is a true two-way street. The other half of the connection is just as profound. A changing magnetic field creates an electric field. Any changing electric field generates a magnetic field, so the fields keep creating each other. On and on. This elegant dance is the key to one of nature's greatest wonders. That leapfrogging cascade is an electromagnetic wave. What is an electromagnetic wave? It is light. It is a radio wave. It is a microwave. It is an X-ray. All of these are the same phenomenon, a traveling disturbance of electric and magnetic fields. They differ only in wavelength and frequency. James Clerk Maxwell discovered this. He unified electricity and magnetism and showed his equations predict such waves. His equations also gave a speed equal to the measured speed of light. This is the payoff for understanding fields. Light is not a substance, but a process, a ripple of electromagnetism traveling through space. When you turn on a radio, you're not catching a physical object. You're tuning an antenna to an electromagnetic wave. The antenna converts the oscillating electric field into a tiny current, which is then amplified into sound. This dance between fields enables modern wireless communication and connects our world. Section 6, the first pillar, Gauss's law for electricity. Now we arrive at the four great laws. These are known as Maxwell's equations, pillars of classical electromagnetism. The first is Gauss's law for electricity. In simple terms, it tells us how electric charges create electric fields. It states that the total electric field flowing out of any closed imaginary surface is directly proportional to the electric charge enclosed within that surface. Charges are the sources of electric fields. Let's use an analogy to make this clearer. Imagine a garden hose with a sprinkler head on the end buried under a small patch of sand. The water spraying out of the head is like the electric field, and the sprinkler head itself is like an electric charge. Gauss's law is like saying that if you place a bucket upside down over the sprinkler, the water flowing out from under the rim depends only on how much the sprinkler inside is shooting out. The simple equation for this law can be written as electric flux, charge enclosed, constant. The term flux is just a way of measuring the total field passing through our imaginary surface. This law is incredibly useful because it lets engineers and physicists calculate the electric field from a charge distribution. For instance, a charged metal sphere. Outside the sphere, the field behaves as if all the charge were concentrated at the center. Field lines begin on positive charges and end on negative charges. If our imaginary surface encloses a positive charge, there will be a net outward flux. If it encloses a negative charge, there will be a net inward flux. If there is no charge inside, every field line that enters must also exit. Net flux zero. It's a powerful and elegant accounting rule for the relationship between charge and the field it produces. Section 7. The second pillar, Gauss's law for magnetism. The second of Maxwell's pillars is Gauss's law for magnetism. It looks very similar to its electrical counterpart, but it reveals a deep, fundamental difference between electricity and magnetism. The law states that the net magnetic flux, the total amount of magnetic field flowing out of any closed surface, is always zero. There are no exceptions. A precise mathematical way of saying what we've observed empirically. There are no magnetic monopoles. You can never find an isolated magnetic north pole or an isolated magnetic south pole. Let's return to our sprinkler analogy. Gauss's law for electricity told us that we could have a source of water, a charge, inside our bucket. Now for magnetism, this new law tells us that there can be no magnetic sprinklers or magnetic drains. If you place your imaginary bucket anywhere in a magnetic field, the amount of magnetic field lines entering the bucket will always be perfectly balanced by the amount of magnetic field lines leaving it. This is because magnetic field lines do not start anywhere or end anywhere. They always form continuous, closed loops. They emerge from a north pole and loop around to enter a south pole, continuing through the magnet to form a complete circuit. The simple equation for this law is as stark as it is profound. Magnetic flux, zero. This zero is not an approximation, it is an absolute. If you take a bar magnet and cut it in half, hoping to isolate the north pole from the south pole, you will be disappointed. What you get is two smaller, complete magnets, each with its own north and south pole. No matter how many times you cut it, you will always end up with magnets that have both poles. Section 8. The third pillar, Faraday's law of induction. The third pillar is Faraday's law of induction, and it is here that the dynamic interplay between electricity and magnetism truly comes to life. This law describes how a changing magnetic field creates an electric field. If you change the magnetic flux passing through a loop of wire, you will induce a voltage that can drive a current. Imagine you have a simple coil of wire connected to a small light bulb. If you just hold a bar magnet stationary near the coil, nothing happens. The bulb remains dark, but the moment you begin to move the magnet, plunging it into the coil, pulling it back out, the bulb will light up. The motion of the magnet creates a changing magnetic field passing through the coil. According to Faraday's law, this change induces a voltage, pushing the electrons in the wire to create a current, which powers the bulb. The faster you change the magnetic field, the greater the induced voltage and the brighter the light will be. The equation for this law is induced voltage equals change in magnetic flux, change in time. The negative sign is important. It tells us the direction of the induced current, which always flows in a way that creates a magnetic field opposing the original change. This is nature's way of conserving energy. But the key takeaway is the direct link between change over time and voltage. No change, no voltage. This is why power plants work. Whether by burning coal, splitting atoms, or using wind, a power plant's job is to do one thing: turn a turbine. That turbine spins a massive coil of wire inside a powerful magnetic field, endlessly changing the magnetic flux and generating the electricity that powers our civilization. This law is at work in countless smaller devices as well. The simple dynamo that powers a bicycle light uses the rotation of the wheel to spin a small magnet near a coil. The charging pad for your phone or electric toothbrush uses a changing magnetic field in the base to induce a current in a coil inside the device, charging the battery without any physical connection. From the grandest power stations to the simplest wireless chargers, Faraday's law is the engine of our electrical world, a beautiful testament to how a change in one field can give birth to another. Section 9. The final pillar and conclusion, the Ampère-Maxwell law, and a world transformed. We arrive at the fourth and final pillar, the Ampère-Maxwell law. This law completes the circle of electromagnetism. In its original form, Ampere's law stated that electric currents produce magnetic fields. However, James Clerk Maxwell realized this law was incomplete. He saw that if a changing magnetic field could create an electric field, then for symmetry, a changing electric field must also be able to create a magnetic field, even in the complete absence of any electric current. This addition was his masterstroke. This completed law shows us the two ways to create a magnetic field. Circulation of magnetic field, Q, current plus. Change in electric flux. The first part, current, is the original Ampere's law. The second part, the change in electric flux, was Maxwell's crucial addition. This new term is what allows light and other electromagnetic waves to travel through the vacuum of space. As the wave travels, its changing electric field creates a magnetic field, and its changing magnetic field creates an electric field, a self-sustaining process that needs no wires or currents to keep it going. Gauss's law, electric. Gauss's law, magnetic. Faraday's law. Ampère-Maxwell law form a complete and stunningly successful theory of electromagnetism. They explain how charges create fields, why magnetic poles come in pairs, how generators work, and how light propagates through the universe. They are the foundation upon which engineers have built electric motors, radio transmitters, power grids, and the computer chips that process information with pulses of electricity. Every time you use a device that plugs into a wall or communicates wirelessly, you are witnessing these four laws in action. They are the invisible rules that govern our technological age. In summary, we have journeyed from the simple push and pull of static charges to the grand, unified dance of electromagnetic waves. We have seen that electric fields spring from charges, while magnetic fields form loops generated by moving charges or by changing electric fields. And most importantly, we have seen that a change in one field can induce the other, a dynamic relationship that gives us everything from electric power to the light of the sun. These principles are not just theoretical. They are woven into the very fabric of our daily existence, a testament to the power of human curiosity to uncover the fundamental laws of nature and use them to build a better world. The story of electromagnetism shows us that even the most hidden forces can be understood, and once understood, can change everything. So the next time you flip a switch, what other invisible laws are you commanding?